you should be able to understand unsteady flow problems. In this chapter, we are going to study as compared to what we have done so far, that most of the time we consider the flows to be steady. You might have defined them previously in fluid mechanics 1, also in fluid mechanics 2 when I started the first chapter. So I defined what is steady unsteady flow. So now in this chapter specifically we will be dealing with unsteady flow problems. Similarly, we will calculate the time for draining a tank and reservoir, calculate velocity of pressure wave in pipes. So we will study that how pressure waves they set up when fluids flow in pipes, and how to calculate the velocity of these pressure waves. Calculate water hammer pressures and critical closure times for valves. So we will study about what is water hammer. This is a phenomena that is encountered in pipe flows, and because of water hammer pressures are developed. So we will study about how to calculate these pressures. And then because we have valves in pipes for controlling the flow, so because of opening and closing the valves, so these have effect on pressures in the pipe flows. Clear? So we will calculate how to determine these critical closure times for valves. So these are the learning objectives. After completing this chapter, you should be able to have a good understanding about all these topics. First, we study about steady flow and unsteady flow before we actually start the unsteady flow problems. So steady flow, a fluid flow is said to be steady if at any point in flowing fluid various characteristics such as velocity, pressure, density, etc., which describe the behavior of fluid in motion, do not change with time. So what is a steady flow? A steady flow is that in which the fluid characteristics such as velocity, pressure, density, discharge, etc., that describe the behavior of fluid in motion, these characteristics, when they do not change with time, all of them, because if any one is changing, then it will not be a steady flow. So when these flow characteristics when do not change with time, such type of flow is known as steady flow. What I said is that when partial v by partial t is equal to 0, means that the velocity is not changing with respect to time. Similarly, partial rho by partial t equal to 0, partial q by partial t equal to 0, and partial p by partial t equal to 0. So in an example, a constant discharge through a pipe. When we have a constant discharge that is flowing through a pipe which is not changing with respect to time, that is an example of steady flow. Clear? For example, we have this pipe and there is a flow of fluid, and any section you consider here, any section x and x. So for this case, if the velocity at any section that is not changing with respect to time, means that the velocity that is constant, so this is known as steady flow. So a steady flow is one in which all the conditions at any point in a stream remains constant with respect to time, but the conditions may be different at different points. So what we say is that along a stream, a channel, clear? So at any one point you take, for example, I take here section XX, section AA, BB, any section you take, and at that section, if the flow characteristics are constant with respect to time, we say it is steady flow. But the characteristic can be different at different points. Clear? For example, here, the characteristic can be different than here, but at any one instant, clear, at any section, if the flow characteristics, if they are constant with respect to time, so this is known as steady flow. What we studied a full big chapter on pipe flows, so that was all about the steady flow, because we did not consider the change of characteristics with respect to time. Clear?
सर I
Next
think यहाँ
is
पर
unsteady flow. What is the question?
सर स्टेडी फ्लो और लेमिनार फ्लो में तो फिर फर्क क्या है?
Steady and unsteady flow is that is characteristics, they do not change with respect to time. Laminar flow, that is a flow regime. We cannot combine two concepts. We have steady flow, we have unsteady flow, we have uniform flow, we have non-uniform flow, we have laminar flow, we have turbulent flow. These are different terms that we need to define. Laminar flow, we already defined, we study extensively about laminar flow. In laminar flow, what happened? That, for example, you have a velocity distribution diagram. Let's say we have a fluid which is flowing in this pipe, and this is the velocity distribution diagram. So in laminar flow, the fluid particles, they move in laminae. You see here, they move in laminae. The Reynolds number is less than 2000. The velocity which will occur, that will be less. Clear? And so on. That is the definition of laminar flow. So I'm not sure why you want to mix it with this steady flow, that what is the difference between steady flow and laminar flow. I hope your question is clear now. Is it clear?
Yes sir.
Next is unsteady flow. So a fluid flow is said to be unsteady if at any point in flowing fluid, any one or all the characteristics such as velocity, pressure, density, etc., which describe the behavior of fluid in motion, change with time. So in unsteady flow, anyone, this is important, anyone or all the characteristics, if they are changing with respect to time, that is known as unsteady flow. For unsteady flow, you can see that the velocity is not constant. Velocity is changing with respect to time. Partial v by partial t is not equal to 0. Similarly, for density, not constant, for discharge, not constant, and for pressure, not constant. So you can see that they are changing with respect to time. So this is known as unsteady flow. In unsteady flow, steady flow, what we say that the flow characteristics, they change with respect to time or not. When you talk about the density, when density is changing or not, then we have compressible, incompressible fluids. When, for example, velocity with respect to distance is changing or not, then we talk about the uniform and non-uniform flow. And we have the laminar and turbulent flow. So these are different terms that we define. Clear? But when we talk about the steady flow and unsteady flow, so then in that case, if in steady flow the flow characteristics, they are constant with respect to time, and in unsteady flow the flow characteristics, they change with respect to time. Example for unsteady flow, a variable discharge through a pipe. When discharge is changing through a pipe, either increasing or decreasing, so we can say that the flow is unsteady flow. There are two main types of unsteady flow. Number one, when a water level in a reservoir or pressure tank is steadily rising or falling, so that the rate of flow varies continuously, but the change takes place slowly. There are two main types of unsteady flow. The first one is that when a water level in a reservoir or tank it is rising or falling, so that the rate of flow varies continuously, discharge will change. Because you already studied orifices in your fluid mechanics 1, and what was the formula for the orifice? So in that case, what you studied, that for the orifice the discharge, that will be equal to CD, which is the coefficient of discharge, into A, into velocity, which you calculated as under root 2 GH. So if H is changing, then discharge will change. Clear? You can see here that, let's say we have this water tank, and then at the side we have this orifice, and water will flow. So now the depth of water is here. This is the depth of water. Clear? So in this case, when H is changing, let's say the water level is falling, so you can see that the discharge will change. So this is the one type of unsteady flow. But in here, the thing is that the change takes place slowly. The second one is that when velocity in a pipeline is changed rapidly by the fast closing or opening of a valve. So you might have seen that when we open the valve, even in your houses, in the washroom or in the kitchen, when you open the tap, the water rushes through it. Or when we close the valve, so what happens that we suddenly bring the water to rest. We are destroying the momentum of water because the water is flowing in a pipe, and when you suddenly close the valve, what will happen that you suddenly bring the water to rest. So these are the two main types of unsteady flow problems. In the first case, the rising and falling of water level in a tank or reservoir, clear, but that is slowly. And in the second case, by a fast opening or closing of a valve, so the changes that take place rapidly. These two main types of unsteady flow problems we will discuss in this chapter. First, we will discuss about this first type of unsteady flow problem, and then we will discuss this second type of unsteady flow problems. Remember, these are not the only unsteady flow problems. We have other types of unsteady flow problems also. For example, the tidal waves. Clear? Similarly, the flood waves. Floods when occur, so that is essentially an unsteady flow phenomena. But these topics we will not cover in this chapter. We will follow our textbook. So in our textbook, these two types of unsteady flow problems are explained, and we will study about them. Now, the first is discharge with varying head. So we consider this any shaped tank, and the surface area of the tank is AS. This is the surface area. It means this is that surface area. If I consider the surface area, this is AS. The height of water in this tank with respect to this datum, that is denoted by Z in our textbook. So we will proceed with Z instead of H. Clear? Delta Z is, if I take a differential segment here, you can see that if I take a differential change in water level, that is denoted by dz. And then this notation is used to denote volume, the water which is contained in this water tank at any time. So that is denoted by this notation for volume, and the change in volume, that will be equal to AS into dz. Clear? Now when flow occurs under a varying head, when head is changing, now in this case we have this qi, that is the inflow, and q naught, that is the outflow. When flow occurs under varying head, the rate of discharge will continuously vary. So when the head is changing, then in that case this discharge, this outflow, it is a function of z. So if z is changing, then the discharge will also change. So that's why it is unsteady flow problem. Now we consider a water tank with inflow as qi, this is inflow, and outflow as q naught. Let this symbol denotes the volume of liquid contained in the tank at a particular instant of time. Now change in volume during a small interval dt can be expressed as, now we consider that during a small interval dt, volume entering the tank. What is the volume entering the tank? Qi into dt. This is volume entering the tank. We already know that Q discharge, that is equal to, this is equal to volume, we denote by this symbol just to differentiate from the velocity, divided by time. Discharge is volume by time. So from here, volume is equal to discharge into time. So now during a small interval dt, volume entering the tank is qi into dt. Similarly, volume leaving the tank, that will be equal to q naught times dt. Volume entering is qi multiplied by dt, and volume leaving the tank, that is q naught into dt. Now change in volume will be difference of the two. So the change in volume, this will be equal to qi dt minus q naught dt. Difference of the two will be the change in volume. Whatever, we are not saying that these are equal here. So whatever volume enters and whatever volume leaves, so the difference will give us the change in volume. Now if AS is the surface area of volume, this volume here in the tank, and dz is the change in level of the surface, then change in volume is also given by AS into dz. So in the first thing what we determine here is that change in volume, that is equal to qi dt minus q naught dt. Also change in volume is given by AS into dz, where dz is the change in the water level. So whatever the change occurs multiplied by the surface area, that is also the change in volume. So now we compare equation 1 and 2, because equation 1 is change in volume. Similarly, equation 2 is change in volume. So now comparing equation 1 and equation 2, so we get AS dz, this is equal to qi dt minus q naught dt. Now the cases that we are going to discuss, clear? So either qi or q naught or both may be variable. So So it is possible that Q naught is variable, means it is changing, because we are dealing with unsteady flow problems, clear? So Q naught is changing. Similarly, Qi can change, that the rate of inflow to the tank can change with respect to time, or both can change. Qi can change and Q naught can change, or both can change, clear? Q naught is usually a function of Z, as I give you an example for the orifice. So if a liquid is discharged through an orifice or a pipe of area A under a differential head Z, so in that case Q naught is given by this formula. Q naught is given by this formula. Q naught is equal to CdA under root 2gz. You already studied and derived this formula for a small orifice in fluid mechanics 1. So CD is a numerical discharge coefficient and Z is a variable. Because Z can change when outflow occurs, this water level can change. So Z is a variable, clear? So when Z is a variable, then discharge can be a variable. So that's why this is essentially unsteady flow problem. So this outflow, this can be, for example, if we have orifice or a pipe, so then in that case it can be represented by this formula, clear? Similarly, if the liquid flows over a weir or spillway, you already studied notches and weirs, etc. So then in that case, this Q naught can be represented as CL into H3 by 2. Clear? So this is the very general equation. Then you can simplify this for a rectangular notch, for a triangular notch. You already developed those equations. But for a weir or spillway, if you have studied in flow measurements chapter 11 and fluid mechanics 1, this is represented Q naught is equal to CL into H3 by 2, where C is the appropriate coefficient, clear, and H is the head on the weir or spillway. So what we are saying here is that in this equation, this Q naught, it can be represented for any given condition. If we have orifice or a pipe which is draining, a tank can be represented by this type of equation, or if we have a weir or spillway which is draining water from a reservoir, the outflow equation can be represented for this. We already studied about this, clear? Q naught commonly varies with time, because you can see it is a function of H or Z. So that's why when H is changing, Q naught will change. So it commonly varies with time. We consider only the cases where Q naught is equal to 0 or Q naught is equal to constant. This is actually I. Qi is equal to 0 or Qi is equal to constant. So in this equation, what we say is that we have the inflow discharge and we have the outflow discharge. So any case that we will consider, so in that case Q naught, this can be represented by these equations for any given case. Either we have orifice, pipe, or we have weir or spillway, clear? So then in that case, this Q naught, this will be represented by these formulas as you already studied discharge measurement. But in case of Qi, the inflow, Qi we will consider either equal to 0 or equal to constant. So remember, in this chapter in the textbook, the inflow discharge, that is either considered 0 or it will be considered as a constant. But we can have a case where the inflow discharge can be a variable, but that is not discussed in your textbook, clear? If you study another book, for example, uh, hydraulics and fluid mechanics by E.H. Leavitt, that is available in your library in the department, so there you can find that a case is discussed where the inflow discharge is considered as variable. But as far as in Franzini, that the textbook that we will study, so we will only consider cases where the inflow clear discharge that is either zero or either it is constant. Clear? So now we can write down qi minus q naught into dt equal to as into dz, and from here you can see that dt, this will be equal to as dz divided by qi minus q naught. We already discussed this, comparing the two change in volume for the tank. So from here now dt is given by this expression. Clear? So what we can do is that we can integrate. Integrating equation 3 gives an expression for time, the time for water level to change from Z1 to Z2. So in this case here, for this tank, if let's say for example this is Z1, from here to here the datum that we consider, let's say this is Z1, and then this level here which is shown, so let's say this is another level Z2. So if we want to calculate that how much time it will take, if you want to calculate the time it will take for water level to change from Z1 to Z2, how much time it will take, so we can do this here. What we can do that we integrate this equation 3, so it will give us an expression for the time. So what we do is that integrating this equation, you can see here from 0 to t, and the right hand side of the equation from Z1 to Z2, where Z1 is here. Clear? The water level that will come from Z1 to Z2. So now when you integrate, so you already know that integral and derivative, they are opposite to each other, so cancel out, and we get an expression for the time. So now if you want to calculate the time for the water level to change from Z1 to Z2, you need to evaluate this integral. Clear? So the right side of equation 4 can be integrated if qi is 0 or constant. This is what we talk about here. Qi is either 0 or it is constant, and if as and q naught can be expressed as a function of z. Because you can see here we talk about the surface area, so in this case the surface area can change. You see this surface area here, this is the surface area for this situation here. This is the surface area, and if you consider another surface area here, these are not the same. When these will be the same? When we have a uniform water tank. Clear? Either square, rectangular or circular, then in that case as will be constant, but for this given case as is not constant. Clear? So it is a function of z, means that with respect to z it is changing, just like the discharge is changing. So in this case we can evaluate this integral as, and q naught can be expressed as a function of z, and if qi is 0 or constant. This is what we said earlier, that when we follow our textbook we will consider the inflow discharge as either 0 or a constant value. So now if you want to, this is a very general expression, this equation 4, this is a very general expression to calculate the time for water level to change from Z1 to Z2, and you can apply this equation to different cases. Clear? This is now the general expression. So let us apply this to a case. We have a rectangular tank with orifice. So now we consider a rectangular tank. This is now the cross section is uniform, so that's why for a rectangular tank, the cross section remains the same. So that is why AS is constant. Clear? In the previous case, what was the cross section? It was changing, a general case. So for a general case, we say that AS is a function of Z. But now we simplify for this case that now AS is constant. It means that it is not changing with respect to Z. Now here we consider a simple case that we have tank with an orifice at its bottom. So the water level is changing from Z1 to Z2. Clear? And if we are interested to calculate that how much time it will take for water level to change from Z1 to Z2, we can apply this equation. This is a very general equation. Now you can simplify this equation for different cases. Since now AS is constant, discharge for an orifice, because here we say that the flow is occurring through this orifice here. Clear? So discharge for orifice, we already know that this is Q naught is equal to CD A into under root 2G Z, where A is the cross-sectional area of the orifice. AS is the surface area for the tank and A is the cross-sectional area for the orifice. Now whatever is the orifice, we are not saying that the orifice is circular or square or triangular or rectangular, whatever. So that's why accordingly then we can calculate A. So we already studied about this equation that AST is equal to integral Z1 to Z2 AS into dz divided by Qi minus Q naught. So in here what we do is that AS into dz divided by 0 minus, because we consider, let's say Qi is equal to 0. There is no inflow. Clear? What is Qi? Qi is the inflow. So as we said that this we consider as equal to 0. So in this chapter, either it is 0 or you can consider it as a constant. Still we can evaluate this integral with no problem. So we consider this as 0. So now in this case, when you simplify, you see that AS is a constant. So it can be written outside the integral. Similarly, this minus comes here, and this CD A into under root 2G, this is constant. Because for the orifice, CD is constant, cross-sectional area is constant. The orifice size is not changing, clear? And under root 2G is constant. That's why we write down this as outside the integral sign. Anything which is constant can be written outside the integral sign. Only Z is changing, because you can see here we have Z1 and then Z2. So Z is changing, it is variable. So that's why we can write down this Z1 by 2 as equal to integral Z1 to Z2 Z minus 1 by 2 into dz. So now we have to evaluate this integral. You already know from the previous classes, you studied extensively in mathematics how to evaluate this integral. So this will be equal to this expression here. After you evaluate, it will be equal to this expression. So now if we know the cross-sectional area of the tank, clear? So this integral, if you remember this integral, if I can just write down here, earlier you studied that x power n into dx. So what is this equal to? This is equal to x into n plus 1 divided by n plus 1. And if it is indefinite integral, we write down plus c, constant of integration. But if it is definite integral as we have, then in that case we do not write down constant of integration. So this is how you evaluate this here, and then finally you will get this expression. So now if we know that what is AS, we know the coefficient of discharge for the orifice, we know the cross-sectional area of the orifice, and then we can calculate the time, that how much time it will take for water level to change from Z1 to Z2. So this is now a specific equation for calculating the time it takes for water to change from one level to another level. This is now a specific formula. Clear? But this formula, that as I said, that this formula, this is a very general formula, and you can simplify this formula to get specific formula for any given case. And this, for example, you want to calculate that how much time it takes. For example, we have orifice at the bottom of a swimming pool, a practical case. So in that case, even this is practical, but a more interesting case is a swimming pool, and you want to calculate that how much time it takes to completely empty. So when you want to completely empty, in that case, what will be Z2? If we want to completely empty, then in that case, Z2 will be equal to 0. This is for complete empty. So Z2 will be 0. You put Z2 equal to 0, and then you just simplify this equation. You will get the time to completely empty the swimming pool or even this tank. So this is how we just simplify this general formula for any given specific case. Now you can apply this to, if you have a reservoir and you want to calculate the time for change of water level in the reservoir from Z1 to Z2. So then accordingly, you just simplify this equation, and in that case put Q naught for the weir or spillway, and then simplify this equation, so you will get a specific equation that will be applicable to that case. So remember, this is a general form, and then this general form we can simplify for any given specific case. So let us solve a problem on this, that we just developed the expression for discharge with varying head. So now this is a problem from your textbook. So in this case, what we have is that they refer to problem 12.1. So in problem 12.1, we have outflow from a reservoir with vertical side is over a spillway. So now for a spillway, the discharge equation is given by this. Q is equal to CWL H3 by 2. So CW is the coefficient for the weir, L is the length, and H is the head of water clear over the weir. So initially there is a steady inflow, so that the height of the water surface above the spillway is Z1. If the inflow is suddenly cut off, prove that the time required for water level to fall from Z1 to Z2 is given by this expression here. From where this expression we can get, we just simplify here. This general expression here that we develop, you just need to simplify this now for a weir. Just like I show you, and we did it for a water tank, you can simplify this equation for a weir. Clear? So this is part first, that prove that the time required for water level to fall from Z1 to Z2 is T equal to this expression. And part B of the question is that how long will it take theoretically for outflow to cease entirely? Means that Z2 is equal to 0, because Z2 If the flow is going to cease on this orifice, what should be the water level? Zero. Because if any level exists, flow will occur. So Z should be zero. Similarly for the where, clear? In this case, H we are denoting by Z. So Z2 should be zero. Then in that case, flow will cease. It will stop. And the third part here is part C in this question, that given the crust of the overflow spillway is 30-meter long, the value of CW in this equation, that is if given 1.91, and the constant water surface area is 65,000 cubic meter. It is AS, which water is flowing over the spillway. With no inflow, it means that Qi is equal to 0. This with no inflow means that Qi equal to 0. Find the time required for water level to fall from 900 millimeter to 300 millimeter above the spillway level. So now in this question we have three parts. In the first part we have to prove this equation for a spillway, and then in the second case how much time it will take for flow to stop, outflow to stop, and for a given in part C how much time it will take for water level to change from 900 millimeter to 300 millimeter over the spillway level. So in this case what we have, that Qi is equal to 0 and Q naught, the discharge outflow, that is given by CWL into Z3 by 2. This is for a spillway, clear? So this is the general expression that we put here. T is equal to integral Z1 to Z2 AS dz divided by Qi minus Q naught. So this is now equal to minus CWL into Z. We have this as the general expression that we already discussed. We have this integral. So we have Z1 to Z2. We have AS into dz divided by Qi minus Q naught. So now this formula, when you simplify here, you get this expression here. Qi is equal to minus Q naught, so minus CWLZ. Now we need to evaluate this integral. So when you evaluate this integral, this is the formula that we get for the time required for water level to change or fall from Z1 to Z2 for this spillway. So for this spillway, this is now the specific formula as we already derived for a water tank in the previous slide. So this is part A. They say that you derive this formula here. Then in the part B, it says that how long it takes theoretically for outflow to stop. So for outflow to stop, Z2 should be 0. Clear? Because after Z2 then is 0, then there will be no water flow. If head is 0, if Z is 0, then Q is 0. So that's why when Z2 is 0, then what will happen? So you put Z2 here, 1 by 0, infinity. So time is infinity. It means that according to this expression that theoretically we are discussing, it means that theoretically the outflow would never cease. It means that you require infinite time so that the flow can stop. But this is not practically the case. Clear? This is theoretically you get this answer. So theoretically infinite time is required for flow to stop. So what could be the reason that we get this unrealistic result? You see, we get unrealistic result. If Z2 is 0 in a reservoir, there can be no flow. So flow will cease in finite time. But now theoretically we get an unrealistic result, that infinite time is required for flow to stop. So what can be the reason for this? So factors which make this theoretical answer unrealistic include the surface tension, surface ripples, evaporation, and seepage losses, etc. Because you already know that from in the reservoir we have evaporation, we have leakage, seepage losses that go down through the soil. So these we did not consider when we develop these expressions. So these are the factors because of which we get this unrealistic result. And part C of the question is that how much time if CW is 1.91 and AS, the surface area, water surface area is 65,000 square meter, and QI is 0, no inflow, how much time it will take for the water surface to fall from 900 to 300 millimeter. So we have this expression and we are going to develop this expression. So now in this case AS is given, L is given. How much is L? 30-meter long. This is given and CW is given. Now Z1, Z2, clear, 900 millimeter and 300 millimeter. So you can put the values and we get the time to be this much. How much time it will take for water level to drop from 900 millimeter to 300 millimeter? 29.2 minutes. Next, this is problem 12.15 in your textbook, chapter 12. So a 25 millimeter diameter smooth brass pipe. The diameter of the pipe is how much? 25 millimeter diameter smooth brass pipe, that is 300-meter long, drains an open 1.2 meter diameter cylindrical tank. This is cylindrical tank, 1.2 meter diameter, which contains oil having density this much and viscosity this much. The pipe discharges at elevation 30 meter. The pipe discharges at elevation 30 meter, means here at this point here, at this elevation here, this is 30 meter. This is 30 meter. Now what is the question? That find the time required for oil level to drop from elevation 36 to 32 meter. Now what we need to calculate is that this is 36 meter here. This is 36 meter. And how much time it will take to drop to 32.5 meter. So let's say this is 32.5 meter. So this is the question. So how to do it? First we check if flow is always laminar in this pipe, because now oil, we are dealing with oil. So first we need to check that if flow is laminar, which is flowing through this pipe. So when V is equal to V maximum, the maximum velocity, the elevation of oil in the tank is 36 meter. Clear? Why? Because when the head is more, the velocity will be more. When the head reduces, the velocity reduces. Clear? You already studied about this. So we say that V is equal to V maximum when elevation is here, this one. When the elevation is here, the velocity will be maximum. Clear? So then in that case, the difference of level between this 36 meter and 30 meter. Clear? This is 36 meter and 30 meter. The difference that will be given by the friction head loss. We ignore the minor losses, entrance to the pipe, etc. If we consider the major head loss. So 36 minus 30 will be equal to the major head loss. So from here 36 minus 30, that is equal to 6, and this is equal to F into L by D V square by 2G. Now assuming laminar flow, for that case we already know that F is equal to 64 by R. This is the friction factor for laminar flow, we already studied, and Reynolds number is equal to rho Vd by mu. So if I put this R here, put this R here, and then put this F here, so what we get is that we get here the expression is equal to 49.4 times V. 6 is equal to 49.4 times V. You just put values, plug in the values. Velocity we don't know. All others data is given. So this is equal to 49.4 times V. Now V is equal to V maximum 0.1213 from here. Clear? 6 equal to 49.4 times V. So from here V is equal to 0.1213 meter per second. Why it is V maximum? Because we consider this as 36. If you reduce from 36, this velocity will decrease. This 30 is constant. This is the pipe elevation here. This is constant. This you cannot change. The water level can change. So if the water level can go down from 36 to any level, what will happen? The velocity will be then less than that. So that's why this velocity that we calculated, this is the maximum velocity. Now that we know this maximum velocity, we can calculate the Reynolds number. Everything is known. We can calculate the Reynolds number. So when you calculate the Reynolds number, it is 96.1. So since it is a pipe flow, so for the pipe flow, we said that if it is less than 2000, then the flow is laminar flow. So since R maximum is less than 2000, minimum will be further less than this. Other values will be further less than this. The maximum R can have is 96.1. Since it is less than 2000, so it means that in the pipe flow, the flow is always laminar flow. So now in general, any elevation minus 30, because I said 30 is fixed here. This 30 is fixed. Now you go up, any elevation, 36, 46, 56, and so on. What we can write down is that in general, elevation minus 30 will be equal to 49.4 times V. Because this elevation minus 30 was equal to 49.4 times V. Here it was 6 because we took elevation minus 30 is 36 minus 30. So you get 6. So now 30 is fixed. That's why this is fixed. Any elevation minus 30 will be equal to this. And then you consider any elevation, you can calculate the velocity V. So from here, this V is equal to elevation minus 30 divided by 49.4, or this elevation minus 30, this can be written as H. Any difference of level can be written as H. So V is equal to H by 49.4. Now we have Q, the discharge. So Q is equal to A into V. Area is given pi by 4 into D square. What is 0.025? This is 25 millimeter diameter of the pipe. 25 millimeter diameter of the pipe. Keep units consistent. So 0.025, and this is V. V is coming from here. So it means discharge is a function of this H. Clear? So now we already stated that Q into dt, which is volume, this is also equal to volume A into dH. Negative sign because this quantity is decreasing with respect to time. So that's why this is with a negative sign. So this is volume and this is volume. So if you want to calculate dt, this will be equal to minus A dH by Q. And you just need to now integrate this equation. You get expression for dt. Just integrate this equation to calculate the time. Clear? You put all the other values. So 0 to t dt is equal to 6 to 2.5 into dH by h. Now dx by x is log of x. So that's why log of h. You already studied how to evaluate this integral in mathematics. dH by h is log of h for the limits. Now this limit is 6 to 2.5. How it comes? Here this difference is how much? This is 6. And now the water level to come from 36 to 32.5 meter. So this is the level here. And this level is how much? This level is 2.5 meter. 32, this minus this, 2.5 meter. So the water level to come from 6 to 2.5 meter, this is what we put here as the limits for this integral. And now you just put the limits and calculate the time. So because we have laminar flow, the velocity is very, very small. That's why you can see that it takes around 27.7 hours to change the level from 6 meter to 2.5 meter. Next we have another problem. We have a cone-shaped tank which has the shape of the frustum of a cone with a zero point 0.2 square meter orifice. This is the orifice here. This is the orifice for which the discharge coefficient is given 0.60 in the bottom. Now the diameter D1 is given 12 meter. This is 12 meter. This is 12 meter. D2 is given 5.6 meter. This is 5.6 meter. And Z0 is 10.4 meter. This Z0, this is given as 10.4 meter. So the water level outside the tank is constant, clear, at section 2. It means here that if we have any water level tank here, that is constant, it's not changing. How long will it take the water level in the tank to drop from section 1 to 2? So this is section 1 here and this is section 2. How much time it will take for water level to drop from section 1 to section 2? Also it is given that the tank diameter is equal to ky, where k is some constant because the diameter is variable. Clear? So d is equal to k times y, and y, this is equal to z plus h2. So this is y here, this is h2, and let's say this is z. So then y is equal to z plus h2. This is given in the question, where z is the variable distance between surface levels. So now we have to calculate that how much time it will take for water level to draw from this section 1 to section 2. Now in this case you can see that we cannot use the equation that we developed because that was a rectangular tank and the cross section of the tank was constant. So here the cross section is changing. So that's why we have to calculate the area that is in terms of z variable. It is not constant. So how to do that? From here you can see that h2 divided by z naught, this is h2 divided by z naught, this is equal to d2 divided by d1 minus d2. This ratio is constant, just like we compare the similar triangles. So h2 divided by z naught is equal to d2 divided by d1 minus d2. This is h2, this is z naught. So this is equal to d2. Here diameter is 0. So that's why we do not write down here d2 minus 0. And this will be equal to divided by d1 minus d2. When you simplify, so in this case, I will show you another method for this also. This is one of the methods. Two methods can exist, then anyone simple for you, you can follow that when you solve the problems. So from here, h2 is equal to d2 into z naught divided by d1 minus d2. So h2 is equal to 9.1 meter because all these things are given. So now h2 is known. Z is variable, clear? So we already given in the question that y is equal to z plus h2. This is given in the problem statement. This is the problem from the textbook. So in here you can see that y is equal to z plus h2. You can see in this diagram. So now h2 is 9.1 meter, that comes here. Z plus 9.1 meter. Now we are already given that the tank diameter, that is equal to k times y. This is also given in the question because the diameter is a function of the depth y. Clear? So this k equal to d by y, k is equal to d by y from here, which is given in the problem statement. So this 12 minus 5.6 divided by 10.4. What does this mean? What we have written here, that this is actually the k. This is actually your k. D by y or d is equal to ky. This is given. What we are given? We are given d is equal to ky. So now d is variable. You can see here the diameter, that is variable. So k is given by this equation, that in 10.4 meter the value changes from 5.6 to 12. So that's why 12 minus 5.6 in a distance 10.4. So how much can be if y has any value? This is how this expression is written, that in 10.4 the change in diameter is this, multiply by y, then we can calculate the diameter at any distance. Clear? So this is d is equal to now 0.615 times y. This y you can come here. If I remove this y, then from here d will be equal to, for this now, d will be equal to this into y, or 0.615 times y. So now diameter is variable. You put any value for y, you will accordingly get the value for the diameter. So now AS is the surface area. This is pi by 4 into d square. AS is equal to pi by 4 into d square. What is d now? 0.615 times y. So this is what we put here, 0.615 times y whole square. So now area is a function of the depth, AS. Because the tank is not of constant cross section. If it was constant, you get constant value for AS. But it is a function of the depth. So now y is equal to what? We already calculated that y is equal to z plus 9.1. This is y. So now we replace this y by z plus 9.1. So now your AS becomes 0.297 into z plus 9.1. Now inflow is 0. This is given in the question, and outflow, because we have orifice, so this will be equal to CDA into under root 2 GZ. CDA, these are given. G is 9.81. Z is 1.2. 1 divided by 2, or square root of Z here. So now Q naught, that is equal to this expression. Now we have this formula that earlier we developed, a general equation. Integral AS dz divided by Qi minus Q naught. So AS is here. This is your AS dz. Qi is 0 and Q naught is given by this expression here. So now what we are asked to calculate the water level to come from here to this level. Clear? So from 12 meter to 5.6 meter, you can do the limits from 12 meter to 5.6, or we can say from 10.4 meter here to 0. This is 10.4, clear? This is Z naught. So 10.4 to 0. So we can, that's why we write down the limits as 10.4 to 0. And you evaluate this integral now. So after you evaluate this integral, you will get the time is equal to 605 seconds. You can convert into minutes and hours. As I said that when we calculate this AS here, and this AS comes because of this procedure here, you can see you get this AS here. Similarly, there is another way to look into this, and that is that your diameter, this will be equal to 5.6 plus this factor. Why? Because here this is 5.6. This is 5.6 meter. And in here, what is D1? 12 meter. So this is equal to 12 meter. Now this diameter will be equal to 5.6 plus this term, which is a function of Z. So 12 minus 5.6 by 10 multiplied by this Z. So let's say Z is equal to what? This is Z here. From here onward it goes. Z is equal to what? This is given 10.4 meter. So if I put here 10.4 meter here, this is 10.4 meter. Not 10. So now you can see if you put here Z as 10 meter. So this if you put, just check if this equation is correct. If this is 10.4 meter, so this cancel out with this, and then this 5.6 cancel out with minus 5.6, and you are left with 12 meter, which is D1 is equal to 12 meter. So this is another approach. You express diameter as this. Clear? Now you simplify, we get the diameter is equal to this. You simplify from here, and then AS is equal to pi by 4 d square. You just put this diameter, and when you simplify, AS is equal to 0.297 into 9.1 plus Z, which is same as this equation that we get earlier. You can see here this and this are the same. So any approach you want to follow, you should get the same answer.